Hey guys, welcome back to another episode of Simuleo. So today, something weird happened when I started up the stream. Sorry about that. Let me go ahead and fix that issue, and then we'll go ahead and get started directly after that. Thanks so much for coming in, guys. Again, I apologize for starting just a hair late, but it's not that late, so I don't think it's that big of a deal. The issue is just simply that OBS, for some reason, did not want to see my camera. I have no idea why. I don't know how to fix that. Every once in a while it happens, so I just kind of roll with it when it does. Okay, so what are we doing today? Today we're going to be working on the dynamic Huffman encoding scheme, which is kind of what we've been working on before, except this time we're actually going to hit it as hard as we can. I don't know how far we're going to get. We'll see what happens. I kind of got the feeling that it's going to turn out kind of poorly. But first, let me do my best to describe the algorithm that we're using. The algorithm itself is not intuitive, so please bear with me as I go through it, because there's going to be a situation that doesn't make a lot of sense. So let's go ahead and open up Zernal, and let's get started. So starting with the basics, and that would be general Huffman encoding. So general Huffman encoding is pretty simple. There should be an image somewhere either that way or that way. I'm not sure which direction I have to point. I think maybe that way. And that is an image of the visualization that we've done so far for basic Huffman coding. Okay, here's what happened with that video. So I made the video. I thought it was great. Hey guys, Jordan. I thought it was great. I really liked the video, but you know, it seemed to confuse a lot of people. And when it got on Reddit, it was just torn to shreds. And so, if a whole bunch of people who know a whole bunch more math than I do think the video is not good, then something had to have gone wrong. I don't know what was wrong. I have absolutely no idea. But apparently, it just was a bad video. So, the videos aren't for me. I just went ahead and took it down. There's no reason to fight about, you know, something like that. It's not like this is my living or anything like that. So we'll see how it goes from there. Yeah, I know it's a little bit disappointing. But that's how it is. I did not change the volume at all. However, I can look into lowering it. Let me see. How's that? Is that a little bit better? I don't know. I don't know what the music sounds like. Okay. Yeah, no, honestly, I thought it was one of the best videos I'd made on my channel. Just period. I thought it was a fantastic video. Patrick OMG, let me know if the volume's still too loud, and I can turn it down from there. That said, I don't know. It's a situation where I didn't want to fight about it. Let me see. I can't hear the music right now, so I don't know what you guys are hearing on the other end. So I guess I'll just try to up it a little bit again. I don't know. One second. I usually try to have, I don't know, something like this maybe. See, I don't know. I can't really place this. I have no idea. Watch one of your older videos, and now I understand what's going on here regarding compression. Watch one of your older videos. Cribib, too quiet. Okay, one second. Let me see. How about I just up it up to a level? Where was it before? Something like this. Is this good? Who's unhappy? One second. Oh, okay, I see what you're saying. Math next. Hey, the Mad Dave. Okay, so how's this for the music? Is everyone happy with the music now? If you don't like the music, that's fine. Wait, well, now the music is off. One second. Okay. Is this too loud? If it's too loud or too quiet, it's fine. Okay. Is this the same level as it was before? I don't remember. Fine. We'll just... How's that? Is this fine? Whatever. Okay, I just spent the past 6 minutes working on... let me know if this is too loud. Okay, so the Mad Dave says it's too loud. It's just, I don't know. I'm gonna leave it here. How's that? Is that good for everyone? I'm sorry about the music, guys. Again, I can't hear what you guys are hearing, so it's kind of hard for me to guess the level at which the music needs to be at. I suppose what I could do, I haven't added any keybinds. Okay, thanks, Gusterman. Gusterman says it's perfect. We'll go with this. Good. Thanks, guys. Okay, one other note. I don't know what's up with my throat today. It is just killing me. So if my voice starts to go halfway through the video, let me know, because you don't have to let me know. That's just what's going to happen at some point. Anyway, let's get started. We're kind of a little bit late. So Huffman encoding. As always, we start with a brief description of the system that we're working on, and then we'll go from there. Huffman encoding is a method in which we use to decrease the total number of bits used to encode a string of letters. Okay, that was super confusing. Let's just put it this way. Let's say we have the phrase hello. We want to encode this using the least number of bits. There we go. That's what we want. Why? Simply because data compression is incredibly useful. How do we do it? Well, we can do this in a number of ways. I'm going to be drawing the Huffman trees here from left to right. However, you'll see that that pattern changes in just a bit. All we're going to do is we're going to go through this string once, and we're going to say, okay, how many H's, E's, L's, and O's are there? By my count, this is made of 40% O's, 20% H's, so L, sorry. L, H, 20% E's, and 20% O's. Okay, so now we add the nodes together down here. So this will be a 0.4. Add these guys together to make 0.6. Add these guys together and make 1. And now what we do is read through the tree. So we say all of these guys are 1s and these guys are 0s. 1, 0, 1, 0. And then we create a table. So L is going to be going backwards, 1. H is going to be 0, 1. E is going to be 0, 0, 1. And O is going to be 0, 0, 0. Good. So now if we were to read in the phrase hello, hello now becomes 0, 1, 0, 0, 1, 1, 1, 0, 0, 0. That is our encoded phrase. Now, you might be thinking, this is not exactly the best encoding phrase there is out there. And in practice, or in principle, there are other encoding schemes that are probably better. Dang it. Let me see. I have no way to check. Gosh darn it. This is a pain. 1 second. It's not that much. Oh, just the H, E, and O. Okay. I can't check. Gosh darn it. I hate not being able to see what you guys see. Okay. Maybe there's a way to do it. Okay, but I think the only thing that you guys are missing is the H, E, and O over here. You can totally... Well, wait. You can beat 2-pass Huffman with adaptive coding. Yeah, okay, so the columns that are hidden, this is an H, E, and O. That's what you guys are missing, L. Okay. So, there you go. Good. So now let's do new page before. The next thing we want to do, also notice by the way the compression works, it is a play on the binary bits, such as the most frequent characters has less bits. Yes, that's exactly why we do it this way. So that is a quick note about Huffman encoding. No matter what we do, rather, if we do 2-pass Huffman encoding, the characters that have the most characters that are used the most in the string that we're using will have the least number of bits. Another thing to note is that the code that we're using is something known as prefix free, which basically means that L is not found in H, E, or O, at least within the starting characters. So we can't directly represent L in the first character of H, and we can't directly represent L in the first character of E or O. Same with H. H doesn't come at the start of L, E, or O. and E doesn't come at the start of O, H, or L, so on and so forth. The idea is that none of these letters are a prefix for one of the other letters in the encoding scheme. This is incredibly simple for decoding, because now if we're decoding the string, we start with a 0, which means we have to be one of these three guys. And then we say 0, 1, so we're at an H. So the first one's an H. Then we say 0, 0, 1. Well, 0, 0 means we're either at E or O. 1 means we're definitely at E. Then we have a 1. Okay, that's fine. That can only be L. Another 1, that can only be L. And then 0, 0, 0, which can only be O, right? So we go through and we just say, okay, we keep going until we find a match. And that's basically how we do the decoding. And because the code is prefix free, it's not ambiguous, it's pretty easy to work with. Okay, new page 4. Now what are we talking about? Well, let's take a second to talk about what we're actually implementing today, which is dynamic Huffman encoding. Okay, so what does this mean? Well, dynamic Huffman encoding is a little bit different than, well, the Huffman encoding that we just saw. The Huffman encoding that we just saw was 2-pass Huffman. We go through once, and then we go through again. Dynamic Huffman encoding does it a little bit differently. Instead of going through the entire string once and then finding the number or finding the frequencies, we go through the string kind of. So here's the idea. We're going through, and we are, what am I saying? Yes, so now we're going to create the tree as we're going through the word. 2-pass Huffman actually achieves optimal encoding for the string you generated the character statistics from. Yes. There are some situations where dynamic Huffman encoding works better than 2-pass Huffman encoding, though. And there are some situations where you have to use dynamic Huffman encoding. But you can certainly imagine a scheme where dynamic Huffman encoding... Anyway, let's go through and let's describe the algorithm. So there are plenty of ways to do dynamic Huffman encoding. The idea here is simply that we create a new tree for every set of characters. So if we do hello again, we'll have a tree for H, we'll have a tree for HE, we'll have a tree for HELL, another tree for HELL, and finally HELLO. So in the end, when we're encoding this one phrase, we'll have a total of 5 different trees. I could have sworn, unless I was completely wrong here, I could have sworn that dynamic Huffman encoding is better for certain strings than static Huffman encoding. 1 second, let me think. Hey, Frank. It's okay, man. Again, just... It's okay. Okay. So, let me go ahead and pull out a quick paper real quick. I think it's in my backpack. 1 second, let me find it. Give me 2 seconds. Okay. Has it decrypting hash passwords? So that's not what we're doing, Frank, but thanks for that. 1 second. Let me take a look. Okay. So the paper from Vitter, sorry, I just hit the microphone. Let me see. I could have sworn it says that the scheme beats dynamic, or it beats static Huffman encoding. That's kind of... Let me see. Anyway, I'll take a look at it one last time. Okay, let me bring this backpack over here. Anyway, let's go ahead and describe how this tree works. I don't. What? What do you mean you don't know if I'm being sarcastic or not, Frank? I mean, I'm clearly. What? I said that's not what we're doing. We're not doing any. We don't do any type of hacking, any type of really anything that could be considered malicious at all on this particular channel. Passwords, definitely not. We don't do any of that. We don't do any. We don't know any of that. Okay, so let's go through and let's go ahead and start creating this tree. So here's our phrase that we're encoding. The first tree that we make is just a tree with an H in it. Okay, this is a pretty simple tree to work with, and I'm gonna do this kind of in a way that is not exactly the way we're going to be doing it later. And the way it works, let me see. I'm just going to go do this the naive way in which we create a new tree every single time step. And then I'll show you that there is another method that is the method that we'll be using. Okay, and the reason I'm going through this in detail is simply because we here, I'm doing a very bad job of describing how the vidder algorithm works. It's not the most intuitive algorithm to work with to begin with, so it takes some time to think about. And I want to make sure it works that way. Frank34, I'm sorry, I can't help. Okay, so let's do the first tree, which is just going to be a 1 and an H, which means no matter what, H has to be a single letter long, so we'll say H is going to be 1 in that case. Okay. Now, the next one, we have an H and an E, so 2, H, E, there we go, 1, 0, fine. Now we do H, E, L. In this case, we do exactly what we did before. We do, we create our tree, so now we have something like, I don't know, maybe 3, H, E, L, and it's 1, 0, 1, 0, something like this. QTP moist. Are you making fun of OIST, or is that an image on the internet? Let me see real quick. That is an image on the internet. Fantastic. My stream seemed down for me, but is it up for all of you guys? I hope it's up for all of you guys. Okay, the next one we add an L, so we'll say 4, L, 0, H, E. And then the last one we have, let me see, L, 0, H, O, E. Okay, and so let's get this right. This should be a 5. This should be a 3. This should be a 2. And there we go. We have 5 added up together. What did I put there? I don't know what that circle is for. So, James, MIT license means I can sell you stuff, right? I mean, MIT license means that you can do whatever you want with it. Just don't hold me liable for it. So that's okay. I was tipping my fedora. Oh, I see. That's fair enough. Okay. So, here's what we got. Thanks for coming into League. So, this is a tree that kind of resembles the tree that we had before. So, let's go down here. Where is the tree we had before? Here's the tree we had before. EOHL. It's actually the exact same tree we had before. And that's great. Awesome. Fantastic. However, this is not the easiest thing to do. So, no, you cannot claim ownership. It just means that you can fork it and you can use it and everything. I think you have to give me, you have to say that, you know, the code is from me to begin with or something like that, or it's been modified or something. I'm not sure. But the point is, you can use most of the stuff in my Simuleos directory. In fact, most of my code you can use for whatever you want. But I cannot be held accountable for anything, and that's fine. And attribution, yeah. No, the new license, unless I'm completely wrong here, the new license would mean that everything that you do in the future has to be open source, which is not the same as the MIT license. So the MIT license is a little less restrictive. Yeah, that's fine. Yeah, that's fine. Okay, so now let's start talking about the next algorithm, the vidder algorithm. this is the algorithm we're going to be trying to implement. Rhythm. And this one's used in a whole bunch of different schemes. Now again, as was mentioned before by Gustorn, the idea here is that we don't have the string beforehand, so we cannot use two-pass Huffman encoding. So, what is a Vidor algorithm? Let's go and start by drawing a tree. We have a root node, and we have, I don't know, 2 other nodes down here, 2 other nodes down here, and I'm going to notate these guys down here as squares. Okay, so now what's next? Anyway, so what are we going to do next? What we're going to do first is we're going to implement something known as implicit numbering. This means that the root node is the highest node, and we count this way. So we go up in this direction and up in this direction. So we'll say we have 0, 1, 2, 3, 4, 5, 6. And there we go. This is our tree, where every single character or every single node in this particular tree has a number associated with it. Now, these guys down here are in essence letters, so we could say, I don't know, A, B, C, D, and that's perfectly fine. They add together into internal nodes, which all have weights, so we'll say these are weight 2, 2, and this is of weight... no, Frank, I did not tell you could sell it. I told you you could do whatever you want with it, which is a little bit different. Okay. So, now we have these guys added together. And just to make this a little bit easier to understand, what I'm going to do is I'm going to add the weight of each individual node right here. So we're going to say 1A, 1B, 1C, 1D. So this is a phrase that we've encoded A, B, C, D with standard Huffman. Okay, so that's what this is. Okay, let me turn down the air conditioning real quick. So, we just encoded this. Now, we have an implicit numbering scheme, and now we have to introduce the idea of blocks. So, blocks are all internal or external nodes that have the same weight. So, for example, these guys are all in the same block. These guys are all in the same block. And this guy is in his own little block up here at the top. Including without limitation, the rights to use. I mean, no one's gonna buy it, but I suppose, yeah, you can sell it. Anyway, so we do this. And what does this mean? Well, this means we have all these different, I guess you could say, data structures to move through. And these structures are not real data structures, but they're just kind of implicitly... Patrick OMG, Huffman is not new. No, this is not new. Dynamic Huffman, this guy right here, what I'm going to show you, I think is new. So, just for the record, Patrick OMG, I realize you might know this, but this algorithm is a little bit hard to understand. Okay, so that means we have 4, 2, and 1 as our different blocks. How does this algorithm work? Okay, let's go ahead and go through and show you everything we need. There's one more thing we need. Yeah, that I forgot to mention. There is an a function here called increment and slide. Okay, increment and slide basically does what you would think it would do. We move this character right here, we move it to the front of this block here. And then we slide all the other ones back. So the idea is that we move it to this position here. This becomes an A. And then these become D, C, and B. So what ended up happening here is A moved to the start of the block. It incremented itself by 1 to be a 2. And then everything else moved back. And that's what happened. We incremented it, and we slid everything else back. Page, new page before. Okay, so let's go from there. I know you can't, it's public knowledge. You could sell it if paired with your own broader software package. Okay. Yeah, I think that's right, Soup Theory. Okay. So how does this algorithm actually work? This is going to be a little bit complicated, so you guys might need to pay a little bit of attention, and feel free to ask any questions, comments, concerns, anything at all you have. I'm going to do my best to go through this as slowly and as thoroughly as possible, but it's still kind of confusing, and I've got to admit I don't know the best way to sell this product or sell this this algorithm yet. Hey Marion, what's up? You could actually resell MIT licensed stuff, you just have to give it attributions. Yeah, fair enough. Okay. So what are we going to do next? Well, let's go ahead and take our string, HELLO, and let's do the dynamic Huffman code. The first thing we do is we start with the root 0 node. Now, the root 0 node is just a 0 node. It doesn't have anything to it. And we first check, is this H, the very first H we have here, is this H already in the tree? Obviously, because we only have a root node, it's not already in the tree. So what we do is we add 2 new branches, a new 0 node over here and a new leaf node, which is just an H. My coding does maybe need a little bit of fixing. Okay, so now what we do is we number everything. So 0, 1, 2, okay? And then we take this block right here and we ask the question, is this guy, we'll say node at the front of its block. Okay, that's the question. And it is, so we don't have to worry about that at all. All we have to do is increment each of these guys by 1. 1 here, and this will be, I guess I'll notate it this way, H1. Okay, so now the next one, we have an E, and I guess I'll do this in pink. We ask ourselves, is this E already in the tree? And it's not, so we add 2 new nodes down here. An E 0 node and a 0 node here. Okay, is the root node equivalent to the null character at the end of the character array? Actually, I'm not sure. The root node is no, definitely not the root node. Actually, in fact, we don't use the root node for the actual encoding here. So the idea is that at the end, similar to what we have here, 1 second, here, or even further down, here, the encoding strings, though we use the root node in order to find the encoding strings, the root node is actually never in the encoding strings themselves. So the encoding string here is L, 0, I'm sorry, the encoding string here is 1, 0, 1, 0, 0, 1, 0, 0, 0. Yeah, I hope that helps explain the situation. So, we added a new 0 node, we added a new E. 1 second. If you don't code object-oriented, how am I supposed to sell this stuff? Fair enough. Okay, so what's next? We add in a 0 node, and then we ask the question, is this node right here, is this node at the front of the block? And in this case, it's not. Because this guy's going to be incremented by 1, it's going to be 1 next. So what we want to do is we want to split it up, or switch it with this guy here. So now our new tree is going to look something like this. It's going to be 2, H1, over here. Then we do 1, E1. And then we have our 0 node again over here. Yeah. And one last thing. Oh, sorry, soup theory. Oh, good. Yeah, OO is object-oriented. Sorry about that. So now we do the implicit numbering again. 0, 1, 2, 3, 4. Okay, so here's where things get a little bit complicated. I'm going to do this one, I guess, in blue. We're going to ask, is this L already part of the tree or not? It's not, so we add in 2 guys here. It's going to be a new L block, which is a 1. I'm sorry, a 0 to start. Now, if I wake up tomorrow, are you going to change that MIT license now so you can so I can rebrand your stuff? No. No, the MIT license stays. There's no reason to change it, I don't think, because you know this particular project is just about going through a whole bunch of random algorithms. The code itself is super messy. If people want to glean some sort of information from it, to use it in some way, that's fine by me. I don't see any problem with that. I'm a big advocate of open source licensing whenever possible. Though I do think GPL is a bit of an exaggeration, or a bit rough in certain cases. Okay, so let's go. So we just had an L0. Okay, so now what we need to do is we need to move this 0 node in front of all of the leaves of weight 1, okay? So that means we need to move it in front of this guy here, and also in front of this guy here, okay? Well, if we move it in front of this guy then needs to be slid back here, and this guy needs to be slid over here. Does this make sense? This is doing the increment and slide thing I said before. We move this guy up forward, and then we move these guys back and back. So the new tree, new page before, is going to look like this. We have a 3 at the top for the root node. We have 1, L, 0 node again, 2, H, E, 1, 1, 1. Okay. Open source software doesn't really have any drawbacks, and GPL enforces that. Yeah, the problem is I think if I'm doing GPL, I'm legally obligated to force people to use open source from there on out, which I think can be a little bit hard. Open source are how people are supposed to make money if you release stuff for free. I mean, that's actually a fair argument. A lot of people do open source code for a living, and the question is, how do you live off of open source code? I mean, ideally, every bit of code that I write is open source, but you know, I've had to work with closed source code before, and I'm a scientist, right? So you'd think that I could just keep all my code open source without too much problem. But the truth is, it's hard. You have to find an appropriate career that allows you that will pay you to do the open source and stuff like that. It's the purpose of dynamic Huffman encoding such that you determine the data is shown more often on the fly, as opposed to building this out by reading the entire data set. Exactly that, MathNX. So the idea here is if we have, let's say, a string that's hundreds of thousands of lines long, dynamic Huffman encoding can go through the entire string letter by letter at the start of things. We don't have to worry about any of the two-pass stuff. We don't have to go through the string first. We can just immediately start with the encoding. And that's what makes it absolutely beautiful about that. You don't have to enforce GPL if you start using it. It just gives you an avenue if you want to. Fair enough. Okay, so now we have a couple more characters left, and let me just go ahead and write down the phrase that we're encoding over here, H-E-L-L-O. So we've done the H-E-L. Now we're moving on to a bit of a, sticky subject. We're now going to encode the phrase H-E-L-L, and we have to ask the question, is this L, hey Witty Bats, is this L already in the tree? In this case, it is totally already in the tree, and we have to do something special here. Good. Okay, so now we have to do something a little bit special. We're going to have to increment this guy's weight. However, anytime we're incrementing a leaf node's weight, we have to do one thing first in order for this to work. And it's not exactly trivial as to why we do this. What we need to do is switch these two nodes before doing any of the incrementing or sliding. Okay, so that's what we're going to do. This is now going to become an H1, and this is going to become an L1. Now, you might be asking why we need to do this. It's because the very next thing is increment and slide. And increment and slide, we increment it, I think I've been messing this up. It's slide and increment, not increment and slide, but that's fine. The idea is that we move through the next set of nodes. So because this is a leaf node, it's going to have to move through the internal nodes. However, if you remember before, when we did this here, our internal node moved in front of all the leaf nodes. Does this make sense? So you move through the opposite type of node that we have. Now by switching H and L, the very next node is a leaf node, right? So if we do our implicit numbering, we have 0, 1, 2, 3, 4, 5, 6. And 3 is right next to 4. Okay, so here's where things get a little bit annoying. We now need to switch this L with this one node over here. So this guy is going to go over here. Okay? This guy then has to go over here, right? That's the only place for it to go, which means our new node system is going to look like this. It's going to be, 1 second, 4, L2, 2, E1, 1, 0, H1. Okay, now this is, I'm actually not sure what Huffman is. I'd have to look it up. I know that the Vitter algorithm is the fastest dynamic Huffman encoding method, but again, I don't know much more from there. I apologize for that. Okay, so now we have this situation here, and this is, I believe, correct. Let me check, and it is in fact correct. Yep, this is exactly right. The paper that this is coming from, the Vitter paper, actually does go through and, how do I put this? It does A, B, C, D, D, which is the same as we have here, H, E, L, L. Now we have to do the last one, which is an O. So thinking about this, the tree can only get so deep that it takes as many bits as raw characters, right? I don't know if that's an exactly stated theorem. What I would say is that it wouldn't make any sense. Thanks, Witty Bents. It wouldn't make any sense, I suppose, if we exceeded that number of characters. I'm not sure, though. The neat thing about this, and I will point this out, is that right now we have H as taking up the most number of characters. So if we go through and do the encoding, H will be the largest character here. However, big O notation for determining the speed of the algorithm. Yes, that's what, actually, I'm not sure. Yes, the soup theory, big O notation, determining the speed of the algorithm. Yes. For the record, it's basically, big O notation, the best way I had to describe it is, yeah, complexity, you're right. Like, if you're going through a list, it's the number of objects you need to touch every iteration, or something like that. So, for example, if you're going through a list, and you have to touch every single object, in order to do the operation you want, it's going to be O, N, N being the number of objects. So, that's kind of the easiest way to think about it if people are confused. For non-sorted lists, it's n squared log n. I'd believe that. That seems about right. Okay, so we have H1 here, and this is going to take the most number of characters. However, it kind of makes sense that this takes the most number of characters, right? Because, in this case, how do I put this? Oh. Sorry for the yawn, guys. In this case, we are probably not going to be using H again for a while, right? So that kind of makes sense. Okay, so now we have to do the O. Let's go ahead and do that. Like before, let me go ahead and color this in green. And let's say we need to create a new 0 node over here and a new O node over here. Now, unfortunately, my O's look like zeros. So just trust me on this one, that it is an O, not a 0. Ivoca Static 78. So far as I'm aware, I'm not Spider-Man, but thanks for the comment. Unless it's a clever way to do this without sorting. I don't think we're sorting. I don't think we're sorting at all. Anyway, okay. So we have 0, 1 here. Now, what do we need to do? Well, we need to move this node right here in front of all of the nodes, leaf nodes, in the block 1. So let's see, what do we have here? Let's go ahead and go through and count. We have 0, 1, 2, 3, 4, 5, 6. Okay, so we need to move it in front of this node here. There. You were actually, the non-sorted would be O, N, I think. Okay. You do sorting O, N, log N, and then, okay. So, we need to move this guy in front here. So, this is going to make the new tree look something like this. It's going to be, let me make sure I'm getting this right. It should be 5, L2, 3. Then we do the internal node here, which is going to be, oh, and one thing to point out, this guy then moves over here, and this guy moves over here. Okay, the internal node here, then we do a 1, 0, 1, 0, 2. Then we should do H1, followed by E1 over here. Okay, and that should be that. So here's our new tree for the phrase hello. You'll note a couple of different things. Witty Pants, you're totally fine. Good. So one thing to point out here is this tree is dramatically different than the tree we had before. That said, it's still a tree, and more than that, we did it without having to know what hello was beforehand. So that's the neat thing about this algorithm. We can go through and create the tree as we're going through. And this obviously has plenty of applications. Anytime you're doing any type of string encoding or something like that, this means you don't have to go through the string to start. And this means that we can do things much more efficiently. Rather, we can do certain things that we couldn't do before. And that's important here. Now, one thing I want to point out is that this particular algorithm is not, how do I put this? It's again, as I said before, not easy to understand. So if you've got any questions, I'm going to go ahead and pause for just a second to see if you do. But if you have any questions, let me know right now and I will answer them as soon as I see them in chat. I also need a quick drink of water because, as I said before, my throat is killing me today. Good. Frank, I am taking kind of a break from physics on this channel. I didn't intend to, it just happened. I wanted to do dynamic Huffman because I honestly like Huffman encoding. It's super fun. And I wanted to do dynamic Huffman because it's one of those things that I've done analytically before, but I've never done it in code. And it's just, I don't know. I find data compression, coding theory, information theory, I find them incredibly cool. Like, of all of the different types of mathematics I've done before, those are the types of mathematics that I really do appreciate and I find incredibly important. Out of curiosity, you get up really early in the morning. When do you get out of bed? Oh, when do you get to bed? I usually get to bed around, it depends. I feel like on every math lessons, I have no idea what's happening. Elite Noob, if you have any specific questions, let me know. Could this somehow apply to neural nets? Let's hit the questions one step at a time. What time do I go to bed? I try to get to bed, let's see, I get up at 5 in the morning, so, well, 4:30 in the morning, so if I get to bed at 8:30, that's 8 hours of sleep, so I typically try to go to bed at 9:30 or 10, that's typically the time that I go to bed. Let me think. However, I normally don't get to sleep until about midnight, so I'm usually lacking in sleep the next morning. Could this somehow be applied to neural nets? You know, I don't know. Right now I'm not seeing a connection, but maybe there is a connection that I'm not aware of. So maybe there's something here. Just be sure, at the 8-bit level, the total number of possible variants is 128. So if the data you're reading has more values, then at some point you need to store data as is. You can use Huffman as the theoretical best to calculate the error. Yes. Let me think. What do you mean store data as is? Sorry, MathNX, I'm not sure I fully understand what you mean by that. So let me think. So if the data you're reading has more values than at some point, in Voga Static, if you have any questions, let me know. Again, I can't really answer any questions if they're not posed to me in the form of either text or chat in some way. You know, I need to be able to see the question. Okay. But if you guys have further questions, again, I'm kind of waiting just a second to make sure the questions get through. So if the data you're reading, I'm not Spider-Man. Okay. If your encoding has more than 8 bits, that's the same number of bits as for one raw data character, which I'm assuming is also 8 bits. You use for the data as is. Oh, I see what you're saying. So let's say we have an 8-bit code. Okay. For a letter. And what you want to do is say, at some point it's more effective to just read the letter through instead of using the dynamic Huffman. That could be true. I'm not sure. I'm sorry, I do not intend to resemble anyone in particular. I'm sorry about that. Okay, so you're right. At some point, it may be more efficient just to write out the character. However, one thing I want to point out is that that's probably not going to happen so frequently. So let me think. With 128, let me see. There was some reason. Why do we need to use 8 bits? 8 bits is because there's 128 possible variants, right? Like you said before. I don't remember. Artenos, I am indeed studying in Japan. I go to the Okinawa Institute of Science and Technology in Okinawa, Japan. Let me just open up the blinds. It is a beautiful morning. I can see the ocean. Great, awesome, fantastic. Also, the data is... I'm not a professor, Frank. Also, the data is all text. It just worse because you can encode all text with 7 bits. I'm not a professor, Frank. Please do not... we have a rule against lying in the chat. Don't lie. It gets worse because you can encode all text with 7 bits. I'm not sure. What is it that you're doing, and what is it used for? As a simple answer possible, please. Elite 3 new. What we're doing is something called Huffman encoding. The idea is rather simple. However, the actual applications are super duper broad. So here's the idea. And just to make sure everyone is on the same page, we just went through a super complicated algorithm in order to do a simple, solve a simple question, which is how to do Huffman encoding. And here's what we have to do. Okay, let's see what we got here. So we have Huffman encoding. Now, one thing I want to point out, guys, when I do this in future episodes, I'm not going to take this much time. And thanks, guys. I'm not going to spend this much time going through it, but because this is the first time that we're going through, or rather, we've gone through it before, but I'm really trying to make sure that this is understandable. I'm going to take some time here. So Huffman encoding. Here's the idea. We take a string, HELLO, and we turn it into a string of bits. How do we do that? Well, bits. We can do this in a number of ways. The best way is such that the characters that are used most frequently have the least number of bits, so that we have the most compressed code possible. Does that make sense? So, for example, in hello, we want L to have the least number of bits, because that means that as we're going through, we don't repeat large bit strings. So, here's the idea then. We put down all the characters in basic Huffman encoding in this way. L comes first because it's the most frequent and has a frequency of 0.4. H comes next, 0.2. E comes next, 0.2. And O comes next, 0.2. Now we add things together here. So we have this and this, 0.4, this and this, 0.6, this and this, 1.0. Okay? He's been doing this saying he's a professor? No. So in Vocostatic, it happens a lot. I am not a professor in Vocostatic, and no. One second, Artenos. It doesn't matter how much bits there are. It matters how much bytes there are. Since a byte is the smallest you can access in memory, you can't access the bits. Yeah. So that is partially true here. Huffman encoding is a super old encoding algorithm, right? The idea is that it's how do I put this? It's it was made right after information theory came over here. But how do you know what his accounts are alts? It doesn't matter that his accounts are alts in Vocostatic. No soup theory. So here's the idea. What I did to create these weights, just to be clear, I went through HELLO has 5 characters in it. So let's just do this up here. Hello has 5 characters. So H has a frequency of 1 out of 5 because it's only 1 out of 5. E has a frequency of 1 out of 5. L has a frequency of 2 out of 5. and O has a frequency of 1 out of 5. I hope this table makes a little bit of sense. So the idea then is that, yeah. Let me see, did I answer your question? Yeah. So the idea is that the weights are based on how many characters there are, and we do 2-pass Huffman encoding. As in, we go through once, we find the number of characters, and then we find the number of times each letter is used, and that's how it's done. Okay, so now we go back through, and we read through and we say 1, 0, 1, 0, 1, 0, and we go back through to find the table for all of these guys. So L is going to be simply 1. Reading back from the 1, we're going to have H as 0, 1. We're going to have E as 0, 0, 1. And we're going to have O as 0, 0, 0. And in this case, we have hello encoded as 0, 1, 0, 0, 1, 1, 1, 0, 0, 0. I think we're probably being a bit harsh on him. Poor guy, probably. Okay, so the thing about Frank is that he's incredibly antagonistic towards particular people. I'm only going to say this a few times. He calls people out and says people that, and tells people that, you know, he basically spreads misinformation. It's okay if he has different ideas and he wants to focus entirely on hacking. That's something we don't do on this channel. However, he definitely has been antagonistic towards particularly Gustorn and several other people in chat, and that's kind of the problem. Blue Luster, I totally missed your comment in chat, and of course, guys, if I miss anyone else's comment, let me know, because I'm trying to read the chat, but I also missed a couple of people. I thought you were like using ASCII, which each character is represented by a byte. No, it's a little bit different than that. Okay, so here's our new encoding string here. Blue Luster, that's the one I missed. I'm basically working on I'm working on an encoding strategy for these characters. So now we just did Huffman encoding, standard Huffman encoding. Hopefully this answers, who was it, Artenos' question at the very start, I believe. No, Elite 3 Noob. Hopefully this answers your question up top as to what we're doing. Now, what we're doing next is something a little bit more complicated. We're doing dynamic Huffman encoding. Huffman. Now, when I say this is more complicated, it is much, much more complicated. We went through all the details. It took like 30 minutes. I'm not going to go through the details again, but I will give you the premise. In the end, it's still Huffman encoding. We're trying to find a way to represent all of these bits, in such a way that we use the least number of bits possible. However, in this case, we're going to assume that instead of the phrase hello, we have an incredibly long phrase that is impossible to go through once. Before we said that in hello, we have H with a frequency of 1 out of 5, E with a frequency of 1 out of 5, L with a frequency of 2 out of 5, O with a frequency of 1 out of 5. However, that is not exactly what we see here, right? The issue here is that we have to go through the entire string once in order to get these frequencies for Huffman encoding. And sometimes we're just not able to go through the entire string once. Sometimes we need to encode right then and there on the fly. And that's what dynamic Huffman does. It allows us to go through, and instead of creating one big tree and one big encoding map, we're going to create a couple of different... we're going to create a new tree for every single letter we read in. I haven't even been here for half an hour, and I can already tell that Frank is an idiot. Well, Josh42, I think he's a troll, not an idiot. I'm pretty sure he's a very intelligent person. It's the same process of the original Huffman encoding, except the tree is built and updated, optimized in a real time, and more data is streamed in. It's very similar, yes. Okay, so that's kind of the idea here. Dynamic Huffman encoding allows us to go through encoding schemes, allows us to go through and encode all the characters without first reading the string out. Okay, so we've been talking about this for about an hour. I realize we spent the first 10 minutes messing with music volumes and things like that. I would like to take just one brief moment to discuss the video that I put out the other day, just to really Yeah, thanks, Gustorn. Um, just to really mention this, a few days ago I did publish a new video on YouTube that was about the determinant. I've recently taken the video down. Now, the reason is simply because there was some negative criticism, and in particular, some people said there was misinformation in the video. Now, as far as I know, there is no misinformation in the video. However, I took it down for a couple of other reasons. If the video is only confusing people, there's no reason to leave it up. And a few other things like that. Now, I realize this is a contentious thing, and some of you guys really liked the video, and that's great. But I just wanted to point out in some format that I'm probably sticking to this decision and just leaving it out. I might someday put it on unlisted instead of private. I haven't quite figured out how I want to deal with the video. Honestly, I thought it was great, but a lot of other people didn't. So I just wanted to, in some sort of public way, express that's what happened with the video. There was some criticism. Some people said some of the information was wrong. I do not want... I'd rather take the video down than have people assume that some of the information is incorrect. Again, that was kind of how it was. Let's see. Old Bald Nerd. Wait, you listen to YouTube trolls? Dude, they're usually half-wits. Actually, it wasn't YouTube trolls. We didn't have any YouTube trolls. It was when it was posted on the math subreddit that it actually, we got a couple of people mentioning certain things. There were a couple comments here and there. And that's, I don't know. Honestly, they kind of hurt my ego a little bit. I got a little bit upset about it, and I mean, the thing is, here on Twitch, I've got a pretty thick skin for people talking about my coding and things like that, but I don't know, usually my videos go over well, and that one, I don't know, I got like 5 downvotes immediately when it was put on R Math, and just, if a whole bunch of people who are super smart with math dislike it, then, I don't know. Yeah, I know, I did it prematurely, but at the time, just to be fair, it was posted on Reddit at like 9 o'clock in the evening, and I really was exhausted that day. I had to go to bed to get ready for stream the next day, and of course, I missed stream the next day, but it was fine. Yeah. I don't know. I was a little premature with it. I might post a video again later. I might just leave it up, and I might just put a comment, a annotation at the very, very start of the video, just to let people know what's up. Because the idea with the video is that you had already done a determinant before, and that this was just another way to think about it. Yeah, I'm not sure. Honestly, people did leave comments though, and I don't know. I didn't want to lose subscribers over it. You know, I didn't want it to be a situation where all of a sudden people were like, this guy clearly doesn't know anything. And it wasn't worth it to me. That was kind of the thing. I'm sorry. I don't have a very thick skin on this kind of things. Again, I apologize. I know a lot of people dislike the opinion or the idea, but we'll see. Yeah, and that was the thing too, Gustron. Determinants are something that are now super intuitive to me. Honestly, before doing those visualizations, they weren't, but now I totally get them, you know? And so I kind of wanted to share that with people, but apparently a lot of people, I think they misinterpreted the point of the video. The point of the video wasn't to teach people how to do a determinant. It was describing what a determinant was physically, and that was kind of the thing. Anyway, so that was a couple of minutes talking about that. Let's go ahead and keep working on the Huffman algorithm. So now we're actually going to get into the coding. And the coding here is going to be a little bit challenging. I'm just going to let you know that ahead of time. So what you should see right next to me on screen, let me figure out which way I need to point. This way? Yeah, that way. Don't worry about it. I will, we can put the video up a little bit later. I've been meaning to ask, what do you use your Razer Naga for? Oh, my Razer Naga actually has been retired. I didn't realize it was still up there, but one second. The Razer Naga is actually incredibly useful. because it has the number pad on the side. I don't know if you can see it, but it's super useful to have a number pad on the side, because a lot of times I'll be doing calculations or something like that, and it's really nice to have that number pad. My current keyboard setup does not have a number pad on it, and that was because when I originally bought the keyboard, I had my number pad and my mouse, so there wasn't really any reason to have an additional number pad there. We are going to be working with C++ for the majority of this, and a lot of it's going to be using the Cairo graphics library. So let's go ahead and CD into projects, Simuleos, and Huffman. Same thing over here, CD projects, Simuleos, Huffman. And for the record, guys, I want to go over here and very quickly point something out. All of this code is available directly at the bottom of my channel. Go down here to github.com, this link here, and you'll have access to the Simuleos directory. Then it will be under Huffman in here. We're going to be starting working on a new file, which is a vitter file, and I'm going to be honest, it's going to be a little rough. Why is your code so ugly? Yeah, it's not exactly the prettiest code. You can see I've been trying to get better and better with it, but that's kind of how it goes. Anyway, so this is the code. Feel free to look at it. The code is MIT licensed, as you know, because you were here just a second ago and you listened to the conversation with Frank, so that's perfectly okay. Okay, so let me ls here. And one thing to note, before going any further with this, we've been working with this code significantly in the past to do animations of Huffman encoding. So this is kind of what took us all the time. So let me go over here and let me do Mirage frames animation.gif, and let's show what we have so far. I believe you can see this directly under this way. This is the image that you see over here right next to my face. And the idea here is that we're basically doing exactly like what I said before. We draw out all the nodes. We combine all of the nodes, starting with the least frequent nodes, and then we go through and we read each node out into its appropriate bit string. Yeah, it was kind of... yeah. Anyway, so then the idea is we combine all of the least nodes first, and we work our way up the tree. You're right, the Mad Dave GPL is a bit more restrictive. That's kind of, but again, as have been mentioned a couple times here, it doesn't matter what license we use. As long as it's open source, I'm happy. Anyway, so this is kind of the this is kind of the idea. If I share a link, of course it's okay. And yeah, that's a good link to share. It's choose a license. Let me go over here. Oh, oops, that was a mistake. My bad. Let me set this terminal into the appropriate size again. I meant to open link, but I accidentally chose, yeah, open link. That's what I want. This is actually a pretty good site. I've seen it before. It definitely explains the difference between all the licenses. So if you're confused over what a license is or how to use a license, that's good to use there. Okay, so again, what this GIF is showing is it is showing the generation of each of the bit strings. Again, the idea is you add the lowest ones first, and then you go through and you add them all together, or you go through and you read the tree. So everything to the left is going to be a 0, and everything to the right is going to be a 1. And that's how we get these bit strings down here. Good. So now on to the dynamic Huffman encoding. Unless you want to be an admin banning people on a physics Twitch stream. Okay. Okay, so what are we going to do next? One thing to note here, guys, just in case you think that we're being a little bit too rough on someone for on stream, I still get most of the chat, even from banned people over here on the right side. So if somehow something happens, really? Ah, dang. If something happens and you think that you were, you know, banned for a reason you shouldn't have been banned, just, I can still see your messages. So you can try to talk to me through there and we'll see how to go from there. Okay, so let's get started with the dynamic Huffman stuff. So we have to kind of go through and think about how we're going to do this. And the reason I did spend so long going through the dynamic Huffman stuff one more time was just to make sure that we all had a pretty good grasp on things. So if you guys have any ideas on how to implement this algorithm in an actual code, let me know. Here's what I know. We have a couple of different papers to go off of here. Let me see if I can find these papers for you really quick, and then I will give them to you in chat. Oh, really? Oh. You aren't going to use Java. So let me go ahead and give you guys these papers, and then we'll go from there. So I think if I go over here, and I do new tab, scroll down a little bit, I should have this one right here. One second. And this paper here is the original paper by Vitter on, one second. On the design and analysis of dynamic Huffman codes. It goes through the description of the what he calls lambda algorithm, which is the Vitter algorithm, on page, let me see if I can find it, algorithm lambda, one second, it's somewhere in here, 4, so it's going to be 837. The other paper, which is incredibly essential or useful for understanding this, is the following. It is algorithm 637, dynamic Huffman encoding. One second, I think I wanted this one. Yeah, this is the one I wanted. Okay, and there you go. So those are the two papers that are incredibly useful for understanding how this algorithm works. If you want more information, feel free to go to those two papers. It is unfortunate that the best information I can find for this algorithm comes from academic papers, because I know those are incredibly difficult to read for some, but that's how it goes. You know, sometimes you have to bite the bullet and go through there. Patrick OMG, only global mods or admins can IP ban, and to be honest, any nerd worth salt can release and renew. Okay, so what I need to do now is I need to go through and basically describe what it is that they do. So what they do in that second paper that I just mentioned is they go through... Wait, Old Ball Nerd? Something to watch? Okay, so they have a couple of different, I suppose you could say, functions that each block has available to it. So what they say is that every node has a weight. Here, let's go through here. Every node has a weight, a parent, a parity. Now, the parity is a little bit weird here, and forgive me if you can't read my handwriting. I will try to make it a little bit cleaner. Parity is the parent node of the leader block B if it exists. So this is the top of the block. Top of block. And then we have right child. First and last. Oh, wait a minute. Parity is... Oh, top of block or left child. Sorry about that. Next, right child, first, last, previous block, and next block. First, last, previous block, and next block. Okay, now this is one way to implement it. Oh, this is awesome. Last month I had to decompile and migrate a Huffman library from Lua to PHP, so this is awesome to watch. Although you're more advanced. I don't know about being more advanced than anyone here, guys. You'll see my code in a second, and you'll see how bad I am at this. In fact, I imagine that most of you guys are going to quit the moment you see me actually programming. Quit watching, that is. Okay, so these are the functions that we want in our node. By this I mean, these are things that we should be able to look at. Now, last time I was here, which admittedly was a few days ago, because yesterday, quite frankly, I did not stream for personal reasons, and the day before that I was so busy working on my video that I wasn't able to stream then either. So let's go through and work on what we were working on a few days ago. So for this, we were going to open up the Vitter algorithm and go from there. Now, one thing to point out is if I go over here and I type the make command, we should make a new animation similar to what we saw before. Now, what we're going to do with this animation, just because some of you guys may not have seen it before, here we are going through all the images. We are encoding the phrase, Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. Here's the encoding phrase, and this is the phrase after decoding, which you're just going to have to trust me, we did decoding for this. So this is currently what happens when we go through and do the make command. Now let's open up the vidr algorithm, vidr.cpp, and let's see what we got so far. Okay, I wouldn't want to HWID ban on a streaming site. Actually, I don't even know what HWID ban is. I apologize for that, guys. Hardware ID? Is that what it is? What if the person banned shares their computer with another person that also wants to watch Twitch? You know, that's the problem with IP banning people, you know? Or I guess hardware banning people. Would be a better way to deal with people than ban evade, though. Okay, so let's go through and see what we have so far. Right now, I don't really have so much going on. We have slide and increment, which has not been written yet. We have void vidr, which has not been written yet. We have another function called find leader, which is reliant on a vector of internal and external nodes, where external nodes, or internal nodes, sorry about that. And it just finds the leader of each block, and we go through and works with that. So this one was actually written by Gustorn, and I apologize for not commenting that in. Let's go here. Function written by Gustorn. Okay, and in order for this function to work, which is find leader, we're probably going to have to find a vector of internal and external nodes. So what I want to do is, first of all, go back real quick, right and quit, and we're going to git status dot on this particular directory. So it looks like Huffman.cpp and Huffman visualization.cpp have been updated since the last update. So let me go ahead and see what we have there. Git diff of Huffman.cpp. And it looks like, yes, so that's one change. And Huffman visualization, .cpp. So it looks like we did change a number of things here. Yeah, so what I want to do really quick before moving any further, that's fine. I still want to give attribution. What is the person? Oh, okay. So let's go here and let me do git add Huffman.cpp and Huffman visualization.cpp. These are just old commits that I have not done yet. Git commit. And before I press enter, hey Edge226, before I put down enter, let it be known that I've been working on this directory for the past year, and there are a whole bunch of files that I should probably have deleted and haven't. And modified. Sorry about that. This is a very long list of everything that I should have done. So adding, what did we add? Let me run over here. Let me see. So if we do git diff Huffman, what was I adding? .cpp. Okay, let's see. I remember that we added in changed code generation so that right was 0 and left was 1. And then we also added in one more thing. Let me see. Fair enough. Zadison, let me see. Can you even get HWID from a browser? I don't know, guys. You guys are way ahead of me here. I assume MAC address or something like that. Old bald nerd. I'm not sure exactly, but I think so. Okay, so code generation so that it was right to left. And one more thing we did was... added in the ability to visualize weight number not implemented. Okay, right and quit. 1 second, right and quit. Git push. I probably should have said origin master, but that's okay. Good. Okay, so now you have access to the latest code as it is right now. Let's go ahead and keep working on the vidr algorithm. Now, one thing that we have to do is create those, what am I going to say? We have to create those lists of internal and external nodes, right? Now, The question is, how do we create those lists of internal and external nodes? Well, as we're doing the encoding, we should probably just keep track of those internal and external nodes as we're going through. Now, one thing I was going to do just to test the leader of the block thing is I was going to test it with a basic Huffman tree that we've already generated. So I want to go in and I want to basically use the 2-pass Huffman function, except this time I want to rewrite it such that it will give us all of the internal and external nodes. And the reason I want to do this is just to kind of test a couple things for my own intuition as to how we want to move in the future. So if you guys have questions, comments, concerns, let me know and we'll address those as soon as we see them. So let me ls here and let's go into Huffman.cpp. Now you'll notice that this code is kind of long, and if you haven't seen it before, it's a little bit annoying to go through. But it's got all of the essentials that we need. Let me see. Okay. So, and yeah, Mr. Miyagi, I think HWID is hardware ID. I think. Although it wasn't exactly answered. Okay, so we have depth for a search. This goes through and does kind of what you'd expect. Now let me think. Huffman visualization.cpp. What do we want to do there? Well, let me see what we got. Quit vi Huffman visualization.cpp. In here we have a couple of different codes. We have create background, grow circle, animate line, draw external. This is the visualization of the Huffman code. Draw internal, regenerate nodes, draw layers, draw tree. Oh, this seems fine. Man, I'm tired. Sorry about that. So let's go here. And what I actually want to do, I know this is kind of bad practice, but what I want to do is I just want to copy a couple functions into our vitter, vitter.cpp file. And this is a little bit weird, I know, but we already have Huffman working, you know? And I feel like I don't really want to mess with it so much. So let me go into huffman.h. And let's see what we got. So we have position and color, we have struct node, that's all fine. Maybe I should have position color somewhere else. Let me see, ESA client and H1 issued hardware ID bans, but it's a lot of effort to get rid of trolls on Twitch that don't want to give up and keep making new accounts. Yeah. And yeah, I think Jost is right. They're both working on your computer. So what do we need to do? Let's go through and let's work on this. Huffman tree. This is where we hold everything. And what I'm going to do here, I'm not so worried about efficiency at this point. So I think what I'll do is this. I'm going to add in the following: std vector of node star, and then we're going to have in internal and external. Oops, my bad. External. Okay. So what we need to do then is every time we put something into our external and internal nodes, we need to make it so it's put in based on the weight of the node itself. So we have this, let's see, what do we have here? Boolean, we have this node compare function. Let me see what this one does. I kind of forget. Boolean operator, constant node left, constant node right, constant return left weight greater than right weight. Okay, so this simply means we read in two nodes and we check to see which one's greater than the other, and I think we can probably use that to our advantage here. So we have a couple other functions in here, but these are not necessary here. Let's go into huffman.cpp now. Now we have our internal and external in the overall Huffman guy. I've heard that Blizzard implemented a hilariously effective ban system for Overwatch that can't even be circumvented with hardware changes. Huh, that's pretty cool. I don't really know much about Overwatch, so actually, honestly, I'm impressed with that game. Like, it seems that a lot of people really like the game, and even though I don't play it myself, it certainly seems like a lot of people enjoy it a good bit. Okay, so what do we have here? I have two different depth for searches. Do I need two different depth for searches? I'm not actually sure. Why do I have two different ones? Let's see. Oh, okay, I see. That's fine. Huh. Huffman code, 2-pass Huffman. Okay, let's go through the 2-pass Huffman function. And actually, guys, I feel like I need to leave some comments because I am commentless. Huffman tree, final tree. Final tree is the, I guess that's fair enough. That one doesn't need comments. For size t, I equals 0, I less than phrase dot size. We're going through everything. We're adding to the weight map. So here we're going to say adding weights to, what do I want to do here? Adding weights to the weight map in our final Huffman tree. Okay, next we have final tree weight map, node queue initial nodes. This is going to be, let's see, creating initial external nodes. Next, final tree.root, Huffman initial nodes. Then here's where we actually perform the Huffman algorithm. You know, the funny thing about this is, when we were doing the visualization, it would have been super helpful to have a list of all internal and external nodes. But I refrained from doing that. I refrained it from doing that because I said it was inefficient, and here I am doing it again. I'm just creating a list of all internal and external nodes. Oh well. So what do we do next? Final tree.bitmap, create bits. Yes, so this is going to be creating our map from characters to bits. Let's see, found this article. Doesn't like color highlighting, it's mentioned below. What happened? Why don't you have syntax highlighting? It's a very useful feature, it makes things easier by a lot. It's just one of those things. Let me see, art notes. Thanks MathinX, I appreciate that. I don't use syntax highlighting just because it looks weird to me and I'm not used to it. Yeah. Sorry about that, Gustorn. We don't have an editor command. Maybe I should. Mr. Miyagi, I actually asked myself the same question too, because as someone who doesn't play too many games, I find myself questioning, yeah, why even worry about it? But you're right. A lot of people really do love. Wait a minute. Let me read this. If your mother comes in your room and tells you to clean up the room, you'll do it, yeah, but you don't really like it. That's how I feel about IDEs, syntax hiding, Vim, etc. I also do a lot of work over SSH and love VI. Did I write that or did you write that? Because either way, that's pretty good. I think you had to write that, right? Wait. Or did BPAF write that? Huh. I don't know. Sorry. Okay, for auto key, final tree.bitmap. Okay. If I have synesthesia, I'll add color coding in my head. Synesthesia is super cool, by the way. Actually, in fact, synesthesia was the reason I got into science to begin with. It's a little weird, but that's totally true. Encoded phrase encode. Let's see, final tree alphabet size, bitmap.size. This is good. Encoded phrase is encode. So let's go ahead, doing the encoding of our phrase, and finding the size. Finding, oh, sorry about that. Finding size of alphabet. Oh, you're just going through and making sure this works. Moore's circle. We want the ocean? Do you want me to... Wait, where are you guys getting all the commands from? Moore's circle for plane stress. You know this. No, I do not know that. What's this one about? That's simply some people... Yeah. That's exactly the reason. I like the Apple way of doing this over a fingerprint. Fair enough. I'm kind of stuck on something. I want to put my extra local Twitch command things. Yeah, what exactly do you want with the commands? I think maybe we can help with that. Or do you want it on your own channel? Sorry, I'm not sure I quite follow where you want the commands to be. Okay, so this is our basic idea with the two-pass Huffman. We create a Huffman tree, final tree, and we put the phrase in, which is the phrase that we're reading in from here. And then we go through, we add all the weights to an appropriate, what I called weight map, which is essentially just every single character has its own weight. And we go through and we give all the characters its own weight. Then we go through and we create all the nodes by using that weight map. And the nodes are just going to be all of the external nodes, putting them in the appropriate places. Again, following the animation that we have before. Let me go ahead and run the last mirage. And let's scroll down a little bit. Following this guy right here, all we're doing here is we're placing all the nodes into the appropriate location. So this is this step here. The next step we do is we create all of the, we do the actual Huffman encoding, which is down here. Here's the Huffman encoding to create all of our internal nodes. Then after that, we do, let's see, Huffman create bits. Yep, so we figure out exactly what all of these guys are, and that's this step here, where we go through and read them out and figure out what all the bits are. And then after that, we do the actual encoding. And that's how it is. It's in Tamper Monkey, but JavaScript adds some extra commands for myself. I know we had 4 viewers. Oh, wow, 33. That's pretty good. Kill Simuleo, slow, painful. Wow, Artenos, that is rough. I'm sorry. Anyway, so that's the idea then. We're going through, we're reading through everything. It's all perfectly fine. If you got any questions on this, let me know. Now we have to modify this to give us a list of all internal and external nodes. And for the record, when I say external nodes, I mean these little dots here on the side. And internal nodes are where 2 lines come together. So let's go here. Let's go ahead and clear this terminal because it looks pretty ugly. And let's see, what do we need to do? So I think when we're actually doing the Huffman encoding, where are we here? Huffman encoding. Oh, so here, when we're doing, oh, I'm in the wrong terminal. When we do encode? No, I think when we do Huffman, what I want to do is read in 2 different vectors here, internal and external, and we'll go from there. Yes, I probably do. Yeah, this was a while ago. I apologize for that. In fact, let me just go ahead and do that now before moving any further. Let's see. Rank quit, vi huffman.h. And let's see, color, node, node compare, that's all fine. Huffman code point, Huffman, here are all of these guys. Priority queue. Do you have it up somewhere and a description of the bug? Yeah, honestly, Gustron's pretty good with this kind of stuff, so I definitely trust him with it if you're curious. So let's go here. Let's go here. I'm basically adding in references to all of these guys, so it's a little bit of I don't know how to put it. It's just something I should have done and I failed to do before when I was writing the code initially. Let's see, vector double weights, keys, create nodes. Yep, these guys also need ampersands in front of them. And here, ampersand. Now what's next? Vector node compare. This should be okay. So let's go down here. You generally want things Yeah, I keep forgetting. Every single time I do it, I always keep forgetting. And I know it's bad practice. Hey, I love Twitch, what's up? So let's go here and set this one also to be an ampersand. And I know it. It's like in the back of my mind, I know I should add in the ampersand. It's just every time I write the function, for some reason, especially on stream, I just forget. Every single time. Okay, I think I hit all of them. Let me go down just to make sure. Node, Huffman, initial nodes. Unordered map. Yep, that one's there. Bitmap. Phrase, good. Current, bit strings, phrase. Good. Okay, so let's go ahead and write quit. Now let's go into huffman.cpp. And let's do the same thing we just did, except with actual, 1 second, with the actual functions themselves. Just to make sure, I feel like I missed something. Node compare, SD vector nodes, bitmap and phrase and code. It looks like it's all there. Huffman.cpp create nodes. Wait, is create nodes only an internal function? Let me see. I actually looked at the generated assembly of a lot of birefs and byvalues a while back. Oh, interesting. I think you mentioned that before on stream, though, didn't you? Let me go to huffman.h. I feel like I'm still missing a function or something. In fact, here's what I'm going to do. vi huffman.h over here and huffman.cpp over here. There we go. We have 2 terminals. Let's use both terminals. Huffman.cpp. Okay, so let's go through, make sure they're all by reference, and then we're going to make it one more time just to make sure everything is good to go. And again, guys, any questions, comments, concerns, let me know. I will approach those as soon as possible. Okay, unordered map, char, key weights. Yep, adding in stuff here. If you want to. You do you, man. You do you. Okay. My friend used to say that a lot, by the way. I have a super good friend of mine from back when I lived in Alabama. Absolutely one of my best friends, I would say probably ever. And he used to say you do you so much. I think I actually want root. Let's leave root without an ampersand. There. For some reason I feel like... Do I want root with an ampersand? That means I can modify it. Am I modifying root? No, I'm not. So let's pass it by value or reference. If I recall correctly, it's better to pass types that consist of 4 floats, 2 doubles, 4 ints, 2 longs by value, as long as they're homogeneous. Huh. But 15 dead people in Japan in knife attack. Holy cow, really? That's in Japan. Oh my gosh, I thought Japan was safe. I'm gonna have to look into that after stream. That's a little unfortunate. Gosh. Anyway, here's what I'm gonna do. I'm gonna continue working on stream. I'm not gonna look up the report, but thank you so much for bringing that to my attention. I'm gonna look into it after stream. We have about 30 minutes left in stream, so plenty of time to still get some work done here. Man, that's unfortunate. Like, it seems to me, and I don't know if it seems to anyone else, but at least to me, it seems like the world is just, every place is just messed up right now, everywhere. So let's go here. I mean, as someone who came from the U.S., I know that the U.S. election season this term is just awful. I know that Europe, of course, has been having so many issues with everything. You know, Brexit. I don't know. With Brexit, I don't know. I feel like everything's just yeah, exactly. It is depressing. I thought that Japan was safe, you know, because Japan in general is said to be safe, and I live in Japan, and I had the most pleasant conversation ever with an old Japanese guy at the pool. He said he was like 60 or 80 or something, but he looked much younger. Wait, Mr. Miyagi, did that happen today? Let me go ahead and right quit here, right quit. Let me make it. Okay, so I obviously screwed up with something. Let's go through and fix everything I screwed up. Let's see, what did I do wrong? STD string bitmap. Let's go to Huffman.cpp 117, sorry about that. String bitmap. What's the issue here? Warning, reference to local variable bitmap. Let me see. It's always been, yeah, that's fair enough. I guess I'm just too young. Call overload depth for search is ambiguous. Yes, it is. Let me go through and let me see what we have for this depth first search guy. We have root, current, and bit strings. What else do we have for depth first search? Just for search there. Current and bit strings. Depth first search, current bit strings. Is not liking warning reference to local variable bitmap returned. Let me see. STD string bitmap. I don't know what this means. Let me see. Call of overloaded depth first search is ambiguous. Call of overloaded depth first search is ambiguous. That's totally fair. Let's go to 143. There. So, with a dynamic encoding like this, would Dropbox use something similar to compress data they receive? I'm not sure what people use for the encoding. I know that a lot of people use a encoding scheme known as LZW. It's Limper Ziv Welch, I think. I don't know, something Welch. Try to explain it a bit here. Okay, cool. So this was a discussion in chat earlier. Oh man, it's not. When I try to zoom in, it's not zooming into the image. It's just zooming. Wow, that's good design. Anyway, that's fine. Okay, something to look into, I guess, later. Let's get this Huffman encoding stuff working. So obviously all I did was add ampersands in front of everything. This led to some ambiguities, so let's go through and see if we can fix these up. So included from Huffman.cpp 110, Huffman H, depth for search node root, fair enough. So let me go to Huffman H, vi Huffman.h, and let's see, what line is it? 86. Depth for search node root, that is something I've forgotten ampersand for. Good. Okay, so what's next? Vectors, characters, and doubles. Initial nodes. Huffman tree. I think maybe it'll make now. Let's write this, and let's go over here to make. Create bits is ambiguous. 209. Let me see. 79. Unordered map. Create bits. node root. Yeah. So let's go to Huffman.cpp and let's see. I want to go to 209. Final tree bitmap create bits. So create bits. Oh. Let's see. Create bits. Create bits. Create bits. Node star. Yep. Forgot an ampersand there too. Let's go over here and make. What happened now at create bits? 1 second. Ambiguity in the new declaration. Oh, oops. That's what I did wrong. I put the ampersand in the wrong place. Make. Okay. Oh, dang. I thought it was making. Reference bitmap return. Error ambiguity in the new. Nope. That's not what I want. Error. Invalid initialization non-const reference type. Let me see. From a. Oh, okay. So let's go up here. 1 second. There's also a thing where older generation thinks that the younger generation is as good as the old one. I feel like, guys, if there is any, how do I put this? If you guys are at all angering each other in chat, I expect you guys to respect each other and you know, don't be a jerk. Let's go here. Let me say, I don't know, phrase. We're gonna do std string. Std string phrase, and we're gonna set this equal to Jack and Jill went up the hill, and forgive me for this, guys, to fetch a pail of water. Jack came down. I don't know. Jack filled. I don't remember the phrase. It's something like that. I'm reading it out. I'm really bad. Okay, so now we're just gonna go in here and just put in phrase. So let's do up here, Jack. Next, and let's do, I don't know, 20x. Oh, my bad. That was sarcasm. Don't worry. No, it's okay. Again, I'm not gonna impose any type of issue. Let's do 20x. Oh no. Good. And phrase. Okay. Let me see. That's the one I was thinking of. Also, let me see. This thing since ancient Greece. Again, the Mad Dave, I was, don't worry about it. It's super weird though. I know it makes no sense, but when I see how helpless teens are, oh, children now love luxury. They have bad manners, contempt with authority. Yeah, I mean, it's fair enough. What was it? Juvenoia? Is that what it's called? Let me see. Vsauce did a video on it. I think it's Juvenoia. Yeah, Juvenoia. I think that's what it's called. Feel free to, maybe. The fear and hostility directed by an old generation towards a younger one. Maybe this is what we're talking about. Anyway, let's keep going. So, now you might be thinking we're done here, but we're not quite done here. Let's go into VI Huffman visualization.cpp. Let's go down here to main, and let's do the same thing we just did. So, we're going to create an std string, which is phrase. And it's going to be equal to Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown. Jill came tumbling after. Okay, let's go here. Let's go to the next Jack. And let's do, I don't know, 100x. Delete these guys. And let's add in phrase. Okay, now let's write this, and let's see what happens if we make it. Don't break. Okay, final tree. We're having some issues here. Final tree, that's because I forgot to add in a semicolon at the bottom. And make it. Come on, don't break it. Bam! Got it working. Okay. That's exactly what I want to see. If you aren't a sober female... What? Oh. That's actually pretty good, old ball nerd. Okay. Good. So now we've added ampersands in front of everything. I'm going to very quickly go in and update Huffman.h real quick. So let's go into vi Huffman.h. Let me go down to the bottom here. Where was I? I think I was here. What I want to do is copy this line. Then I want to delete the line. Write this. I want to do git commit Huffman. That was Hiffman. I want Huffman .h Huffman .cpp and Huffman visualization .cpp. Now I'm going to say changing reference passing complicated complex data structures by reference. Something like that should work. Sure, why not? Git push origin master, just so you guys have access to this code before we start changing it. Good. Now let's go ahead and add back in that line, and let's go from there. Oh, let me go in real quick and let me mention something too. Internal. Internal, external. Note, these will used for vitter algorithm testing. Right, quit. Okay. So what I'm hoping to do by the end of today's stream, guys, is get a good testing environment ready for the vitter algorithm so that we have everything we need to work with. Again, any questions are welcome. Comments in chat, of course, welcome. Anything you want to say, just keep it civil. That's the only thing I'm worried about here. Okay, so let's go into huffman.cpp. What I'm going to do is I'm going to go into the make file, and I'm going to comment out the thing that's converting all of the images into a movie at the end, because that will take some time. And now let me go here and let me do vi Huffman. Ooh, what was that? That wasn't what I meant to do at all. Vi Huffman visualization.cpp. And I'm not going to render the frames. Let's go down to main. Go down here. I'm a bit curious. What's endgame here? What will this be used for? Okay, so old bald nerd, let me very quickly mention something. This channel is a little weird in that we don't really have an endgame here. The entire purpose of this channel is just to go through algorithms that are at the level of difficulty that I can't understand them intuitively, and I have to go through and code them. So for the most part, these are physics algorithms because I'm a physicist, but here we're kind of taking a step back, or not step back, we're taking a step in another direction and doing a computer science algorithm. Huffman encoding was something I always knew about, but had never actually implemented in code. Dynamic Huffman coding, again, something I've known about for a very long time, but have never actually implemented in code. So this is kind of the idea. The point of this channel is simply to implement algorithms, and then after we're done implementing the algorithm, I make a YouTube video about it. That's all it is. There isn't an end game, I suppose you could say. But I think there's definitely merit in doing this. Of course, I'm the one doing it, so of course there's merit for me because I'm learning a lot. But that said, I'm hoping that you guys are learning a lot too. I mean, that's kind of the point, that we're learning this kind of stuff together. So I'm going to try to be very, how do I put this, very understandable in what I say. And if there is a day, I'm letting you guys know this, if there is a day that I feel I'm just not, my mental faculties are not working well enough for me to do a good stream, I just don't stream that day. This happened yesterday, and a few days ago it happened, but that was because I was up until like 3 o'clock in the morning editing a video. But that's okay. So draw layers, layer, that seems fine. So we're going to go ahead and right quit this. We're going to make it. And this should do everything except for draw the images. Yes, so it does not draw the images, which is great. There's always merit in learning new things. Keep that mentality. It's more important than anything else. I need to get a quick sip of water, guys. But yeah, as a PhD student, I totally agree. I was actually thinking about it the other day. You know, there's a lot of things I can do with a physics PhD, and a lot of things I can't do anymore with a physics PhD. So keeping that in mind, I was thinking about future career options, and I honestly think a professor would be a good job for me. It's something I'd really like to do, but it's really hard to do. I realize that our kind, maybe that's true. I don't know what you mean by our kind, but honestly, I find learning very enjoyable. it's one of those things. A lot of my friends spend all their days playing video games or watching television or something like that. And I don't know. I always find that if I just have a paper in my hands and I read the paper, it is the most enjoyable thing I can possibly do with my time. Just sitting there, no music, just in the quiet. So much fun. Thank you for that, Patrick OMG. Open link. So the Mad Dave, to answer that question, when you get a PhD, sometimes you're considered overqualified for certain positions. And I just want to point out that some industry positions prefer people with like masters than people with PhDs. And I know quite a few people, at least I've heard from the grapevine, that a few people will not hire PhDs on principle, being that they just don't like academic people. The other thing is too, a lot of times an industry position wants to teach you things, and if they're wanting to teach you their way of life, coming in with experience on another way of life that's not related to their way of life isn't necessarily the best way to do things. That said, there are definitely positions in IBM, Intel, big companies and small companies that are dealing with research, and that's where they want PhDs to be in. It's just, it closes some doors, being engineering doors of sorts and things like that, but it opens up new doors, which are research doors and things like that. So all in all, it's fine to get a PhD. It just shifts your job prospects to be more researchy than engineering in a way, I guess, for physics. For other places such as biology and chemistry, it massively boosts your job prospects. It depends. Soup theory. Let me see. I try to stay active and learn new things. AI is incredibly cool, by the way. It's one of those things I really want to learn. I don't know very much about it. Well, I'm a student in Germany, and I work part-time at an institute. Generally speaking, if you want to be a big manager at a great company here, you better have a PhD. Oh, wow, I didn't know that. That's really cool. In the U.S., I guess I should have said what I was saying before was from what I understand in the U.S. Okay, so let's go ahead and see how far we can get here. All we need to do is create a bunch of internal and external nodes, which should be easy, right? Okay, so let's keep going. Final tree, root, Huffman, internal nodes. What do I need to do? With the Huffman algorithm right here, we have something called Huffman. What this is doing is, if you remember, this is... Great, Zadiston. Yeah. That was an accident. Okay, so what are we doing? Oh, we're going to go through Huffman and work from there. Kind of like did in Boiler Room about how he doesn't want people with experience. Yeah, that's exactly how it is. Sometimes that happens. It's not so frequent. It's just with all of the trained engineers, you really have to sell yourself as a physicist to be an engineer, which makes sense. You didn't go into physics necessarily to do engineering, right? So just things to keep in mind. Okay, and also, guys, yeah, getting personal information from other people is always a sticky subject, so be careful with that, guys. Okay, let's go into the Huffman function. So Huffman, we have decode, Huffman. This might have been the slowest way to go through this. 1 second, I'm looking for the Huffman function. Huffman, decode. What? Did I miss it? Huffman, where is Mr. Huffman? I want a function. Oh, there it is. Node star Huffman. Okay, so we return a node star. I'm going to go through and I'm going to have a vector of other nodes. So let's see. Let's go through and comment this out, see what we're doing. So node 1 in node 2 node parent. Good. We sort the vector by weight. Good. So let's see. Initial nodes.size is greater than 1. So what we're doing here is we have a priority queue, which is just a standard queue, except it's kind of already sorted in a way. And we're going through and we're popping the top nodes. So we go through, we say node 1 is the top, we pop that node. Node 2 is the top, we pop that node. Then we say node parent is a new node that we're creating. and we're saying that the new node is the weight of the other two nodes put together, and it is also pointing to the left and right nodes. So what I need to do here is I need to go through and I need to basically push these guys into internal and external nodes. And this isn't so bad. So what I'm going to do here is I'm going to add in another couple of guys, std vector, and I want node star. And I realize, guys, this is a little inefficient, which is why I do not intend to commit this version in particular to GitHub. The version that's on GitHub right now is for the Huffman.cpp file, unless I forget, the version that I think I'm going to have outward facing for a while. So vector node, and I want internal nodes. Let me go over here real quick, vi huffman.h. Let's go down here to the bottom. Let me see, what did I call it? I called it internal. And let's go down to the next line, and let's do std vector of node star. And let me see, how did I, node star is fine. External. Let's see, you need a PhD to be a manager in Germany? Why would someone with a PhD dumb down their career to be a manager? Okay, so, okay, I'm not going to address this one, because there's so many ways I could do it and so many ways I could do it wrong. Yeah, let me think. My dad's actually a property manager, so I have a great respect for people like that. So, okay, so let's go here and let me see. Where is our Huffman function? Should be Huffman. There it is. Good. So let's go ahead and add in what we need here, which is going to be std vector of node star internal. Then what do I want? I want external. Oh, I forgot a comma. Std vector of node star external. Good. Let me add a comma over here. Now, I'm going to do this in a super inefficient way, and I apologize for that, but let me think here. We have... Oh, come on. There has to be a simple formula to figure out how many internal nodes there's going to be, right? Here, let's go and let's look at this. So let's do page, new page before. If we have the number of external nodes... Oh, thanks, Addison. I forgot. Okay, so we have the number of internal nodes. 1 second. Write this one, write this one. I think PhDs are preferred for people who manage the German branch of a company or hold departments in a company. Okay, you're probably right. You know way more about it than I do. So, good. Okay, so let's think about this. We have a bunch of external nodes. Let's say we have 4 external nodes, okay? If we have 4 external nodes, then we know we have 3 internal nodes, right? Is this always true? Let me think. So let's say the tree looks like this. Okay, so we have external node here, root node. Let's see, 1, 2, 3, 4. 1, 2, 3. Okay. The other way we can align the tree is 1, 2, external node, external node, external node, external node. So let's see if we can find a formula for the number of internal nodes we need if we know the number of external nodes. So let's say we have 5. Well, this means we need 4 internal nodes. Let's say we have 6. How many does that mean we need? We need a total of... Wait. Is it just n minus 1? Is that all it is? That seems... I feel like that's wrong. Page, new page before. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Wow. Is it really n minus 1 internal nodes? That's... I somehow I feel like this makes sense, and yet somehow I feel like it doesn't make sense. So we're going to say it's n minus 1. I think the best managers are those who start from the bottom up rather than top down. Just my opinion. The last word on the subject, I promise. You keep talking about it. I don't care. There's a thing called Peter Principle, aka people rise to the point of their incompetence. I'll agree with that. I know that a lot of people are like promoted when they're perfectly great at doing their own job, you know? And a lot of people, for example, my previous advisor really, really loves physics, absolutely adores physics, and that's fine because he's a physicist. However, now, because he constantly does very well as a physicist, he basically just does management of physics. And though that's great, let's see, is floor of n divided by 2. Let me see. The number of internal nodes in a complete binary tree of n nodes is floor of n divided by 2. So I guess it's correct. Let me think. Floor of n divided by 2. So if we have n nodes, the number of internal... Oh, I see. So that's including internal nodes. Yeah. Okay, we'll go with that. But yeah, so my previous boss now just does management, and he hates just doing the management, but at the same time, he understands that it's a better position, you know, and that's how it typically works, you know, with especially professorial positions. You spend your first couple years doing professorships, and then after that, you kind of taper off. Okay, so let's go through and let's work on this. I'm going to assume that we already have, the higher you go, the less you spend doing what you love. Yeah, that's exactly what I was saying. I totally agree. Okay, let's go down to the Huffman function. And honestly, guys, we might have to call this a day pretty soon. So here's what I'm going to do. The Huffman function was what I'm looking for, right? Gosh, why do I always forget what I'm doing the moment I start trying to do it? Does anyone else have that problem? We're already in the Huffman function. We have to figure out what we call the Huffman function. So let's do Huffman. Huffman. Nope. 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 Nope, nope, nope. There we are. Okay. So creating internal and external node. What do I call this? Internal and external node. Vectors. There we go. So we're gonna say std vector of node star, and this is going to be internal, and we're going to make it of size alphabet size. Now, I know what you're thinking. We don't have alphabet size yet, but actually, since we already have the weight map, we can find the alphabet size just fine. So I'm going to go ahead and find the alphabet size directly after finding the weight map here. So we're going to say final tree weight map.size, which should be the same. Let's go down here, dd, and I'm going to comment this line out, but not remove it directly. Okay, so next line, for any non-empty binary tree with n, let me see, with n0 leaf nodes and n2 nodes of degree 2, n0 is n2 plus 1, unless you love managing old. Let me see. Hey, that your fan? Dude, that's okay. I felt terrible this weekend too, so we're both feeling terrible together. Okay, let me see. Okay, it's on the next line. For any non-empty binary tree with n0 leaf nodes and n2 nodes of degree 2, n0 is n2 plus 1. Good. Okay, so that's exactly what I said before. So let's go here. And let's see. Final tree alphabet.size. Good, we have an alphabet size. So let's go ahead and create the internal and external nodes. This is going to be size alphabet size. 1 second, size. And the next one is going to be external, which is of size alphabet size minus 1. And I'm going to leave a quick comment here with a semicolon obviously at the end saying number of internal nodes is number of leaf nodes alphabet size minus 1. Only teacher took pity on me, I guess, because One question away from a 70 for a C. That's fine. Okay, so let me go down here. Well, it's good that you passed the class, right? That's my dad always said C's get degrees, right? So that's the important thing. So we're gonna do internal and we're gonna do external. Now what I'm gonna do is I'm gonna go over here, right quit, and run a make command just to make sure it makes. It doesn't make. Alphabet size was not declared in this scope. Let me see. Final tree.alphabet size is what we need. Where are we? Internal nodes. Let's go here. Final tree.alphabet size. And let's go down here. And I'm actually just going to define this on the next line. std node star there. Let me see. Thanks. Alphabet size. Final tree.alphabet size. Sorry about that. Okay. Let me see. That your fan. Okay. Write this over here. Make it one more time. Good. This one seems to make just fine. No problems. Okay. Now, guys, we have put forward the skeleton. We've done a good bit of stuff today. We went through. We made sure that we understood the vidder algorithm, and honestly, I think we have a better understanding now than we ever have before, at least on this channel, of how the algorithm works. Now we're getting started with getting this stuff actually implemented in code, and that's what we'll be spending most of the time doing tomorrow and throughout this upcoming week. My guess is that it'll take us a full week to implement the entire vidder algorithm, maybe a little bit longer. In fact, probably a little bit longer to do the visualization with that. So we'll see how far we get there. Let's see. We put the -1 in the wrong constructor. You put the -1 in the wrong constructor. Let me see. Yes, you're right. I did. Thank you. Let's go here, up here, add a -1 here, and remove the -1 there. Is there a reason why you're predefining the sizes of the internal and external node instead of just doing a pushback? At least so far as I'm aware, and this might just be some sort of weird taboo thing. I don't like doing pushback because it seems, or rather I heard from the grapevine, that it is inefficient. So I don't like doing it just because of that. And I realize, you know, what is it? Premature optimization is like the root of all evil or something like that. And that's how it is. I realize that, but I still try to optimize whenever possible. Okay. Anyway, guys, we've done a lot today. I'm going to go ahead and end the stream right about now. I realize, yeah, there's still discussion to be had. And yeah, we didn't get quite as far as I wanted to, but that's okay. I've got to get to my friend's place pretty soon in order to get all of that done, or get some other stuff done. But we have done a lot today. We went through the vidder algorithm. We started implementing simple stuff in code, fixed up some stuff with the Huffman.cpp file, a whole bunch of things here and there, little things. Tomorrow is going to be predominantly programming, just getting everything done, working on the visualization and stuff like that. I like having the visualization over here to the left of me. I think it adds a lot to the stream. That way I don't have to have like the visualization constantly up here. I think it's great. But if you guys don't like it, let me know. Let me see. Pushback is inefficient insofar as it causes... Okay. Anyway, guys, this is what we're working on from here on out. Yeah, maybe there are more efficient ways to do this. I don't know. Anyway, guys, that's it for today. Have a great day, night, afternoon, evening, morning, whatever time it happens to your time. And I will see you around next time for the next episode of Simuleos, where we continue working on dynamic Huffman trees, hopefully getting somewhere with the actual algorithm itself, implementing it in code. Again, we're going to spend a little bit less time with the, how do I put it, with Zernal tomorrow. It's going to be more time just actually doing the code. That's why I spent so long today, so I don't feel as bad for spending less time on it in the future. Let me see. Specifying the size in the constructor is not a good idea. I see. So let me see. I'll look into the reserve stuff too in a bit. Sorry about that, guys. Again, I every once in a while when it comes to this efficiency stuff, I fail really bad at it. So we'll look into that next time. Anyway, guys, I really do got to go for now. So I'll see you guys next time. Have a great day, guys. Bye, guys.